Hello, everyone, and welcome to the Calculus 1 video lecture series. My name is Professor Hunter, and today we are going to be looking at an introduction into what are called limits, and we're going to be looking at what a limit is and finding a limit using a table and a graph. So, to get us started, we're going to look at a relatively familiar concept to a lot of you, which is driving in a car. So let's suppose that you are driving along a highway, and let's say that you travel 30 miles in 30 minutes. So we're going to figure out what your average velocity would be in miles per hour. So if you travel 30 miles in 30 minutes, that means you are traveling at an average of 60 miles per hour. Well, how did we get that 60? Well, you take 30 and you multiply it by 2. Here's another way to get 60 miles per hour. Remember, velocity is just the accumulated displacement over the passage of time. So the accumulated displacement is that 30 miles over the total time that has passed in hours, which is 1/2 hour. Another way that you can think of this is the difference between the ending displacement, which is that 30 miles, and the starting displacement, which is that 0 miles, divided by the length of time that has passed, or the ending time, which was that 1/2 hour, minus the starting time, which is 0 hours. And then in either of these cases, you get an average velocity of 60 miles per hour. Now that is what is called an average rate of change. And an average rate of change doesn't just have to apply to moving cars and to velocity. It can really apply to any function that stands for anything that is changing. So in any quantity that is changing, the average rate of change of that quantity over a closed interval is the amount of change divided by the length of the interval. It should sound like the slope of a line, rise over run, because it really is. So we have this idea of average velocity, which is how fast on average was that car traveling in that 1/2 hour. However, that might be different than what's called instantaneous velocity. So the average speed was 60 miles per hour. Does that necessarily mean that you traveled at that exact same speed for that entire trip? No, you were probably traveling more at some times, less at some times, probably traveling exactly 60 at other times, but the instantaneous velocity, which is the velocity at a one particular instant in time, might be the same as the average velocity, but it might also be different. So instantaneous velocity would be the velocity of the car at any given instant, not over a specific interval of time. So they might be the same and they might be different. So here's another example of average velocity. Let's say that you have a rock that is launched vertically from the ground with an initial velocity of 96 feet per second. And neglecting air resistance, this is the position function for the rock, s of t, where t is the number of seconds after launch. And the graph of s of t is given here, and there are 3 points that are selected. We have s of 1, s of 2, and s of 3. So what we're going to do is we are going to use this equation and the given points to find the average velocity of the rock from 1 second to 3 seconds. So just like we did with the other average velocity example, it is going to be the total displacement divided by the total change in time. So the total change in displacement will be the ending position, which is s of 3, minus the starting position, s of 1, then divided by the length of the time interval, which is the ending time 3, minus the starting time 1. So according to this graph, s of 3 is going to equal 144 feet. S of 1 is given as 80 feet, divided by 3 minus 1. Then you're going to subtract first and then divide, giving you an average velocity of 32. And any applied problem does always need units on your answer. The position units, which are in the numerator, were given in feet. Over, the time units in the denominator were given by seconds. So this is going to be an average velocity of 32 feet per second. Now, if at any point in this PowerPoint that you want to try an example before I go over it, just feel free to pause the video and resume it when you are done working. So what I want you guys to do is I want you guys to use that same graph and that same function to calculate the average velocity of the rock from 1 second to 2 seconds, and then to calculate the average velocity of the rock from 2 seconds to 3 seconds. So go ahead and pause the video and try those two on your own. All right, so looking at this first one, for the average velocity is going to be the change in displacement divided by the change in time. So the change in displacement is the ending position, s of 2, minus the starting position, s of 1, divided by the length of the time interval, 2 minus 1. So s of 2 is given as 128, minus s of 1, which is 80, over 2 minus 1 gives us an average velocity of 48 feet per second. And then for this last one, for the average velocity between 2 seconds and 3 seconds, we're going to have the ending position, which is s of 3, minus the starting position, which is s of 2, divided by the ending time 3, minus the starting time 2. So s of 3 was given in the graph as 144, minus s of 2, which was 128, divided by 3 minus 2, gives you an average velocity of 16 feet per second. Now, for each of these, what I'm going to do is on this graph here, I'm going to draw all three of those average velocities that we just calculated. So going back to this first example, we got an average velocity from 1 second to 3 seconds to be 32 feet per second. Now this should look like the slope formula because it actually is. If you were to draw a line that connected 1 s of 1 and 3 s of 3, the slope of that line would be 32. Then for this next one, if you were to draw a line between 1 s of 1 and 2 s of 2, the slope of that line is 48. And then if you were to draw a line between 2 s of 2 and 3 s of 3, the slope of that line would be 16. And those are what are called secant lines. A secant line on a curve is a straight line that connects any two distinct points on that curve. So the average rate of change of a function on a closed interval a to b is equal to the slope of the secant line that connects a comma f of a and b comma f of b. And this doesn't have to just deal with average velocity. If your function is standing for anything that is changing, the average rate of change in general is just going to be the f of b, the function evaluated at b, minus f of a divided by b minus a. So that right there is the average rate of change formula. It is basically the slope of a line. It is the exact same equation as the slope formula that you learned a long time ago back in algebra, because it is. The average rate of change is equal to the slope of the secant line. They mean the exact same thing. So with average rate of change, the slope of a line is a rate of change. You learned that back in Algebra 1 or whenever you learned about slope of a line. The slope of a line is a rate of change. So the slope of the secant line of a particular function on the interval a to b is the average rate of change from x equals a to x equals b. So that is why the average velocity of the rock was the same as the slope of the secant line that connected 1 comma s of 1 and 3 comma s of 3. So what about instantaneous velocity? What if we wanted to find the velocity of the rock at exactly 1 second? Not between 1 second and 2 seconds, just at exactly 1 second. This is what is called an instantaneous or instant rate of change. Now, here's the problem with the slope of a line formula. You need 2 points. The average rate of change requires 2 distinct points in time. So, instantaneous velocity would just deal with the velocity at only 1 point in time. So unfortunately, you can't use the average rate of change formula to find instantaneous rate of change because instantaneous rate of change only involves 1 point and the slope of a line requires 2 points. So we calculated 3 average velocities. Which one do you think is the best approximation for the rock's instantaneous velocity at 1 second? It was probably the average velocity between 1 second and 2 seconds, which we got as 48 feet per second. That was probably the best approximation of the 3. However, this still isn't good, because for a rock that is moving that quickly, 1 second is actually a lot of time, and a lot of accumulated distance happens in that 1 second. So average velocity, very easy to compute because you just find the slope of the line between the 2 points and that is it. However, this does involve 2 distinct points in time. So how are we going to compute the instantaneous velocity when we just have only 1 point and not 2 points? Well, here's what we're going to do. We're going to go back to this function s of t, and we're going to use average velocity to approximate the rock's instantaneous velocity at x equals 1. So of the average velocities that we calculated, the best one was the average velocity between 1 second and 2 seconds, which gave us that 48 feet per second. However, that is an awfully long time for a rock that is moving this quickly. So this average velocity is not a good approximation for the rock's instantaneous velocity at just 1 second. So how do we improve this approximation? Well, we can improve this approximation by bringing the endpoints closer together. So let's calculate the average velocity between 1 second and 1.5 seconds. Just making that time interval a half a second shorter is actually going to make a huge difference, and you'll see in a moment. So remember, the average rate of change, the average velocity, is going to be the ending position, s of 1.5, minus the starting position, s of 1, divided by the ending time, 1.5, minus the starting time, 1. Now, unfortunately, I didn't give you s of 1.5, so you're going to have to use this function, plug in 1.5 in for t, and find s of 1.5. You should get an average velocity of 56. So 56 feet per second is the average velocity from 1 second to 1.5 seconds. So just taking off that half second changed the average velocity from 48 feet per second to 56 feet per second. So that's a huge difference. I will say, though, that even that half a second for something that is moving this fast is still a lot of time. So the only way to make this approximation even better is to move the points closer and closer together. So here's what I want you guys to do. I want you guys to find the average velocity of that rock from 1 second to 1.1 seconds. And then find the average velocity from 1 second to 1.01 seconds. And then just keep bringing the points closer and closer together. So find the average velocity from 1 second to 1.001 seconds. And then 1 second to 1.0001 seconds. So pause the video and take a few moments to evaluate these 4 average velocities and see what happens. All right, so from 1 second to 1.1 seconds, you get an average velocity of approximately 62.4 feet per second. From 1 second to 1.01 seconds, you get an average velocity of 63.84 feet per second. Then on this time interval, you get an average velocity of 63.98 feet per second. And then on this last time interval, you get an average velocity of 63.99 feet per second. So I think it's probably safe to say that the instantaneous velocity of the rock at t equals 1 is probably 64 feet per second. Because as these time intervals get smaller and smaller, yes, the average velocities do keep changing. However, the amount of change does start to go down. And by the time that these points are in time are very close together, we get an average velocity of almost exactly 64. So you can keep making that time interval smaller and smaller if you want. You will just watch the average velocity get closer and closer to 64 feet per second. So I think it's safe to say that no matter how close you bring these 2 points, the instantaneous velocity of the rock at t equals 1 is 64 feet per second. Now I'm just going to draw a quick visual of what just happened. So we started off with the instantaneous velocity between 1 second and 2 seconds. Sorry, the average velocity between 1 second and 2 seconds. And we calculated the slope of that secant line to be 48. Then we brought the points closer together from 1 to 1.5 and got the slope of that secant line to be 56. And then we kept bringing these 2 points closer and closer and closer together to finally get a slope of 64. That is what is called a limit. So you've actually just found your first limit. In layman's terms, a limit is a function's behavior as one value approaches another. A limit is what a function is doing as x or t approaches a certain value. So what we can do is we can express this phenomenon over here formally using what is called limit notation. So we're going to say that the instantaneous velocity is the limit as t approaches 1 of s of t minus s of 1 divided by t minus 1, and that limit is equal to 64 feet per second. Because for each one of these average velocities that you calculated over here, notice how the starting time remained 1, and it was the ending time that we brought closer and closer to 1. So the ending time, which we would call t, got closer and closer to 1. So formally, mathematically, we will call that the limit as t approaches 1. And then in the average rate of change formula, it was this s of t and this t value here that kept changing. This s of 1 and this 1 remained static for each of these average velocities. So s of t and t is what is kept getting closer and closer together. So we say that this limit is equal to 64 feet per second. Now in my drawing here, as these 2 points got closer and closer together, the secant line between them got closer and closer to what is called a tangent line. A tangent line on a function's graph is a straight line that touches the curve at exactly one point. So while a secant line connects two distinct points, a tangent line just touches the function's graph at exactly one point. And this point right here is called the point of tangency. So back here, as these secant lines got closer and closer to that tangent line, the average velocities got closer and closer to the instantaneous velocity, 64. So the slope of this tangent line would actually be 64 feet per second, also known as the instantaneous velocity. So the instantaneous rate of change, to find the instant rate of change of a function at a point, what you're actually finding is the slope of the tangent line at that point. So the instantaneous rate of change is also called the derivative of the function. So instant rate of change, slope of the tangent line, derivative, they all mean basically the same thing. Now, more formally, here is the formal definition of a limit. So let's say that a function f is defined for all x values near a certain point a, except possibly at a. That's actually important, that as long as x is defined near a, it doesn't necessarily need to be defined at a in order for a limit to exist. So if f of x is arbitrarily close to some y-coordinate L for all x values that are sufficiently close to, but not equal to a, then we say that the limit as x approaches a of f of x is equal to L. So a limit is what a function is doing as x approaches a certain value a. Keep in mind, it's not equal to. A limit cares about what a function is doing near a point, not necessarily at the point. In some cases, they might be the same. In a lot of cases, they won't be. So remember, a limit is what a function is doing as x approaches near a certain point, not necessarily at the point, though there can be some overlaps. So we've already covered how to find a limit using a table. We're also going to cover how to find a limit using a graph. And finding a limit using a graph is actually really easy to do. I'm going to switch colors for this actually. Make it a little bit easier to see. So we can find a limit using a graph by simply looking at what the graph and the y-coordinates are doing as x approaches a certain value. So we're going to use this graph of this generic f of x to find each of these values if possible. So f of 1. What is the y-coordinate that goes with an x-coordinate of 1? Well, f of 1 is equal to 2. That may or may not be the same as the limit as x approaches 1 of f of x. So what this limit is asking is, what is the function doing as x gets closer and closer to 1? What are the y-coordinates approaching as x gets closer to 1? Now, since there are two sides to this, I'm going to look at both sides. So I'm going to trace the graph from the left, and I'm going to trace the graph from the right. And it looks like from both directions they are approaching this point right here. So it looks like the y-coordinates are getting closer and closer to 2 as we approach 1 from both sides. So we say that the limit as x approaches 1 of f of x is equal to 2. So this was a case where the function's value equaled the function's limit. That is not always going to happen. So for the next one, f of 2, what is the y-coordinate that goes with an x-coordinate of 2? Well, that's this point up here, which is 5. So f of 2 is equal to 5. Now remember, a limit asks what a function is doing near a point, not necessarily at the point. So for the limit as x approaches 2 of f of x, what this is saying is what are the y-coordinates approaching as x gets closer and closer to 2? So coming from this direction, if we approach the graph from this direction and from this direction, it does look like the y-coordinates are getting closer and closer to this hole right here, which is at 3. So even though there is no actual y-coordinate here at 3, it doesn't matter. The y-coordinates are getting closer and closer to 3 as x gets closer and closer to 2. So we say that the limit as x approaches 2 of f of x is equal to 3. So in this case, the function's value did not equal the function's limit because a limit only cares about what the function is doing near the point. And then for this last one, for f of 3, what is the y-coordinate that goes with 3? Well, there's a hole right there at 3, so f of 3 is just undefined. And then for the limit, as x approaches 3 of f of x. So even though f of x is not defined at 3, it doesn't matter. A limit might still exist. The y-coordinates might still be approaching something even though there is a hole at x equals 3. So approaching this from both sides, so we're going to take a look at what it's doing from the left and approaching from the right. So approaching from the left and from the right, the y-coordinates are getting closer and closer to 4. Even though the function actually never reaches that point, it doesn't matter. The y-coordinates are getting closer and closer to 4 as x gets closer and closer to 3. So we say that the limit as x approaches 3 of f of x is equal to 4. So that is how to find a limit using a graph. You simply look at what the y-coordinates are approaching as you trace the graph from both sides and let x get closer and closer to that value. Now for this graph, I made sure to look at the function from both sides. So I looked at what it was doing near x equals 1, x equals 2, and near x equals 3 from both sides. If you were to only look at what the function is doing as x approaches a from one direction or only one side, that is what is called a one-sided limit. So we have what is called a right-sided limit, which its notation looks something like this. We will read this as the limit as x approaches a, and then this up here means from the right of f of x. And that just means what is f of x doing as x approaches a only from the right. Then we have what is called a left-sided limit, which has this notation. So this is read as the limit as x approaches a from the left, that's what that little minus sign means, of f of x. And what this means is what is f of x doing as x approaches a only from the left. So in that last example, both the left-hand limit and the right-hand limit, both were approaching the same value. It was approaching the same value from both the left and the right. So if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, if they are equal to each other and they both equal some value L, then we say that the overall two-sided limit as x approaches a of f of x exists and equals L. So basically, if the limit from the left and the limit from the right equal the same value, then the overall two-sided limit exists and equals that value L. So if you don't see either a minus sign or a plus sign up here, if you just see this implies both sides. So look at both the left and the right. Now, if the limit as x approaches a from the left does not equal the limit as x approaches a from the right, then we say that the overall two-sided limit as x approaches a of f of x does not exist. That's only one way that a limit can fail to exist. There are other ways that a limit can fail to exist. We're going to explore each of those in another video lecture, but here's one of them. So let's take a different function, and what we're going to do is we are going to find each of the following limits if they exist. So we're going to start with the limit as x approaches 2 from the left of g of x. Well, there's 2. And we're going to trace the graph, but only from the left, and we're going to see what the y-coordinates are approaching as x approaches 2 only from the left. So coming from the left, it does look like the y-coordinates are getting closer and closer to 4. So the limit as x approaches 2 from the left of g of x is equal to 4. Now for this next one, the limit as x approaches 2 from the right of g of x. So what we're going to do is we're going to trace the graph of g of x only from the right, and we're going to see what the y-coordinates are approaching. So as x approaches 2 from the right, the y-coordinates are constant. They are all 1, and so they are approaching 1. So the limit as x approaches 2 from the right of g of x is equal to 1. Now, since the limit from the left does not equal the limit from the right, then we say that the limit as x approaches 2 of g of x, remember, this would mean from both sides, that means that the two-sided limit does not exist. And DNE is a perfectly acceptable shorthand for does not exist. And if you were ever asked for the reason why a two-sided limit does not exist, it is because the limit as x approaches 2 from the left of g of x does not equal the limit as x approaches 2 from the right of g of x. Now you can find limits using a graph that you will generate on a graphing calculator. One thing I will caution you though is especially with holes. So most graphing calculators, except the newest TI-84 colors, will not show a hole in a graph such as this right here. It would not show this. Only the brand new TI-84 colors are going to show this. So you can also find a limit using the table of values that is found in your graphing calculator. So if you press second graph, you will generate a table of values. If you press second window, which is your table set, you can change the table from going by ones, you can go by a halves, you can go by 1/4. Unfortunately, I cannot do two things at once on here, so I can't show you how to do this on a graphing calculator. I would have to do this in a separate video. So if you need any help with those basic functions on a graphing calculator, you have learned those in previous courses, please just feel free to email me and I will walk you through those. But what I want you guys to do is I want you guys to graph this function here on a graphing calculator and find each of these limits. You are going to need parentheses, especially around the numerator, and you really should have parentheses around the denominator as well. Once you have this graphed on a graphing calculator, it would look something like this. So if you are finding the limit as x approaches 2 from the left of f of x, whether you're looking at the table of values or from the function's graph itself, you will find that from the left, the function is approaching the y-coordinate of 3. Then, if you look at the graph from the right or the table from the right, remember, values to the right of 2 are values greater than 2. Values to the left of 2 are values less than 2. So whether you're using the graph or the table, you will find that the limit as x approaches 2 from the right is 3. So because the limit from the left equals the limit from the right, then we say that the overall two-sided limit as x approaches 2 is also equal to 3. However, if you were to go into the table, if you were to press second graph and go into the table of values and look at what is actually going on at x equals 2, you will find that f of 2 is actually undefined. There is a hole right here at 2, 3. So as long as you remember that a limit is what a function is doing near a point, not necessarily at a point, f of 2 does not need to be defined for the limit to exist as x approaches 2. And the reason why f of 2 was undefined? Well, if you take a look at this, what would happen if you plugged in 2? Hey, you would get a 0 in the denominator. But what I want you guys to do is also take 2 seconds, plug 2 into the numerator. 2 cubed minus 8 is actually 0. So yes, f of 2 is undefined. Undoubtedly, it makes the denominator 0. But what makes this a hole and not a vertical asymptote is the fact that when you plug 2 into every single spot that you see in X, you actually get 0 over 0. So we're going to be talking about 0 over 0 a lot more in the next video when we learn how to find a limit using algebraic techniques, which finding a limit algebraically would not use a graph or a table. It would use some sort of algebraic manipulation to find the limit. So that is what is going to be in the next video. Thank you all very much for watching, and I will see you in the next one.